200. This is chapter 7. We're getting close to another exam, actually, if you can't believe it. And if you look, there's a lot going on. So take a look. Homework, chapter 6, 7, 8, all that's out there and available to get ready for the exam. I've posted activity 3 now, and we've talked about it in office hours with some students. This is a 5-point assignment, but I think this really helps you get ready for the quiz that's coming, the exam that's coming. So come see me during office hours. Those are on Zoom to go over this activity 3. It's not easy to draw these diagrams, so that's why we need to practice. Come see me. Quiz 3, exam 2. So I've graded quiz 3, and you should have your grades and comments. If you're having trouble accessing any of those, please let me know. Exam 2 I'm still working on. Quiz 4, it's going to be over chapter 6 and part 1 of chapter 7, and that's going to be due on April 22nd at the end of the day. And again, if you're considering withdrawing, let me know. So in this first section, we're going to really talk about chemical equations. They come from changes, balancing, stoichiometry. So this is a lot of Chem 152 topics. The part 2 of this chapter will go in a little more detail, maybe some things that you haven't covered before. As I mentioned, things are full. What I mean by that is there's an activity, there's a quiz, there's 2 new lectures. There's a lot going on the week of April 20th. And then the next week is chapter 8, the last chapter before the exam, and then exam 3. So let's get started on this. What I want you to see is that this is a very quantitative chapter. We just left all of this theoretical stuff, bonding theories. There was a few calculations in there of bonding order, but really it was conceptual. So what we're doing now here is heavy calculations. Okay, so grab your calculator and get ready, do some stoichiometry. So first, all this is based on chemical changes. Okay, we're talking about chemical reactions, and then we're going to do calculations based on those chemical reactions. So this is a reminder, state changes, melting, boiling, those are state changes. Those are only physical changes. Even dissolving, we've talked about electrolytes, we've talked about, and we've seen that in lab, conductivity, things dissolving, the ions that form, those are all physical changes. Chemical changes when the atoms rearrange. So that's really what we're focusing on in this chapter. So review, physical, it's water, H2O, it's water, H2O, it's just spaced out. That's a liquid state, this is a gas state, they're much farther apart. So that's what's different there. The other physical examples that can be a little confusing, subliming, just actually talked about this with a friend randomly about your ice cubes at sublime in the freezer. Okay, so if we go from solid to gas, your CO2 solid goes away into the gas forms, or actually your ice solid in the freezer, your ice cube can go away, and your ice cubes it looks like they're shrinking. Dissolving, mentioned that on the last slide. We go from a solid into the aqueous, water was added here across the arrow, and these are dissolved, either molecules or ions, depends on what your substance is. Okay, so where we're going then are the chemical changes. So iron oxide, for sure that's a different chemical reaction. This looks different than the rest. Okay. Propane tank, propane C3H8 goes to CO2 and water. Those look different. Atoms are rearranged. So really just starting to focus and distinguish the difference, physical change, chemical change. So a quick check for you, go ahead and pause the video, read through this, see if you can identify looking at this, if we match lit held under a cold piece of metal, what are these? Are they physical or are they chemical? And if you look, chemical is burning, Okay, if the temperature changes, if we have a physical change, condensation, deposited is the opposite of sublimation, so that's still a physical change as well. So if we're going to write chemical equations, we for sure need to identify, is it a chemical reaction, and then we can write a chemical equation. So which of the following is a chemical process? So rusting, we already solved that one. Freezing is not, that's a physical change. Decomposition of water into hydrogen and oxygen, that's changing the substance, yes. Compression of oxygen, so it's not changing oxygen, it's just compressing it, so that's a physical. So the two chemical are the 1 and 3. So when we get to writing chemical equations, a few things stand out, okay? Got to know the logistics. Reactants are on the left, products are on the right. This goes back to understanding what's a solid, liquid, gas, what's an aqueous, so that's states and mixtures. Our formulas, we spent time on naming substances. Was it an ionic compound, covalent compound, polyatomic ion? Was it a diatomic? Okay, remember the diatomics, these 7, the hydrogen, plus this looks like a 7 over here, these other 6. These are a diatomic. So if we're writing a chemical equation and it says hydrogen, that's H2, or it says nitrogen, that's N2. So we have to know and review our naming to make sure we feel really confident on writing chemical equations. So when we get to chemical equation, really want to emphasize that all of these have coefficients, whether they're written in or not. Okay, so that's 1, 2, 2. Okay, and if we just think about the molecular level, that's a molecule of O2. That's 2 molecules of hydrogen, and that forms 2 molecules of water. So of course we've talked that this chemistry that we're in, we're focusing on the micro and the macro. Structure determines properties, so we're looking at the small scale and the big scale. So that's the small scale, molecules. That's what we, symbols or what that looks like. And now we're looking at the big scale. We want to interpret that as 1 mole, 2 moles, and 2 moles. And again, we've done grams, moles, particles, so now we're going to really emphasize this, balancing chemical equations, converting from one thing to another. And this takes us back to our laws, conservation of mass. That's where this balancing comes out. We have to have the same number of particles on the left as we have on the right. That's conservation of mass. So balancing, okay? Start out, if you have lab at Miramar, you've already been doing this in lab, and so you've got lots of practice already, so we'll just review a few concepts on balancing. As I mentioned, it does come from conservation of mass. It's really important to distinguish between a coefficient and a subscript. Okay, so if we have 2 hydrogen, and remember there's always a 1 out in front here, 1 oxygen, 2 water, that's coefficients. Okay, so that goes to everything. So that goes to 2 H's, that goes to 2 O's. And of course the subscripts just go to the atom that's on, 2 oxygen, 2 hydrogen, 2 hydrogen. If we had a parentheses, okay, then of course the subscript would go to everything in there. There are 2 ammoniums. So this is how we balance, putting out coefficients 2, 5, 2, 2 to get the same number of atoms on the left and the right. We don't change subscripts, okay? So be really careful. Remember, we learned all of these names because that goes with a specific formula. If you start changing subscripts, you change formulas, that changes names. So this might seem ridiculous if you've been doing this for a while, but for an example, H2 plus O2, water, that's a chemical equation. It's not balanced. You can take a look here if you want to do a tally. I put it underneath the arrow. There's 2 hydrogens on the left, 2 hydrogens on the right. And then if we look at the oxygens, there's 2 on the left, but there's only 1 on the right, okay? So if you take a look, well, we need an extra oxygen, so we just throw in an oxygen. No, that's a different chemical reaction. This oxygen atom doesn't exist like this, so that's a bad idea. Bad idea. Well, I need 1 other oxygen. I can change the subscript. Okay, that changes the formula of that product. That changes the name of that product. That is a different product. That's hydrogen peroxide. That's not the chemical equation we're talking about. What we're talking about is hydrogen, oxygen, and water. So we can change right here with a coefficient, and then we can change over here a coefficient. And now if we go back to our tally, we have 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, 2 oxygens on the right. So that's what we want to be confident in, is we're not adding things like this scenario, we're not changing the current formulas, we're only adjusting the coefficients to get balanced. So here's some tips, okay? Balance atoms in more complex substances first. So we'll do some examples of this. The free elements that we just were looking at, like hydrogen or oxygen, any free elements, save those. And clear fractions by multiplying. We'll actually use fractions in balancing in chapter 9, but right now, typical is not to have fractions, so get rid of that when you're balancing. And then, of course, as I was doing, check the total number of atoms on both sides. It's really easy, especially some of those complex ones in lab, to just kind of want to be done, want to go through it. Most of them are balanced. Okay, you can't kind of be balanced. You have to be fully balanced. So check every atom. All right, so here's 3 to practice. So go for it. Go ahead and pause the video and take a look at what you got here. So a couple things I want to point out. Remember we mentioned elements that are by themselves. Okay, so that's hydrogen by itself, sodium's by itself. So those we want to save till last. Also want to point out, if you have polyatomics that are together still, so sulfate and sulfate, you can just balance those as sulfates, or nitrate and nitrate. So you can see we need another nitrate on the right. There's 2 on the left, so balance it that way. But if you have something like this, carbonate, but carbonate's not over on this side, it goes into carbon dioxide, you can't balance looking at just the polyatomics. So you might have to do the tally of individual atoms. So those are just some suggestions on looking at these. So now we'll go in a little bit more detail. Sodium in water gives this nice violent reaction, hydrogen gas. You can ignite it, it's pretty exciting. So if you want to start the process, you can take a look and see that oxygen, we're 1 oxygen, 1 oxygen. Okay, that's good. Sodium, 1 sodium, 1 sodium. That's good. Hydrogen, okay, there's 2 on the left. There's 2, and don't forget this one over here, 3 on the right. So remember how we saved the element for last? You could add a fraction here of 1/2. Okay, that makes this balance now. Some people don't like to work in fractions, that's okay. Anytime that it's not working for you at the first level, you can always scale up. So you could say, well, it didn't work when I had 1 sodium, let me try it with 2 sodiums. You could do it that way. If you did do this half approach, then multiply it by 2, everything gets multiplied by 2, so 2 times 1/2 gives you one of those. So then, again, double check, everything is balanced on both sides. All right, so if we take a look, this is the one I told you, carbonate's on the left, but it's not on the right, so we're gonna need to check each individual. So if you look, then we've got sodium, 2 on the left, and then we can put a 2 over here, our sodium bromide, so our sodium's balanced. Carbon, we got 1 carbon, great. Bromide, so we change this up here to give us 2 bromides, so we need 2 bromides on the left. Double check the hydrogens now. You can see here we've got 2 H's and we've got 2 H's here. So what we did, we double check the oxygens. Now remember, we're counting individual oxygens, 3 oxygens, 2 oxygens, and 1 oxygen. So that's all balanced as well. So how we accounted to balance this were these 2 here. That's it. So sometimes it can be very overwhelming. There's, 5 substances here, but it might be changing 1 coefficient, changing 2 coefficients, but you still need to check everything to make sure you're balanced. The polyatomics that I mentioned, sulfate, nitrate, so that really helps here. They stay together, so you can account for those. So here's the nitrate. If you have 2 of them, then you need 2 nitrates on that side. And if you take a look, that's all we had to do here. So sulfuric acid, barium nitrate gives us 2 nitric acid, 1 barium sulfate, and everything's good to go and balanced. So that's the fundamental step. Do we have a balanced chemical equation? Because now it's all about calculations with this. Okay, so this is stoichiometry. We're changing amounts of one substance to amounts of something else in a chemical reaction. So we have to have a balanced chemical reaction, and then we can determine amounts. So pretty classic example here is octane in our cars, and you probably have heard carbon dioxide is a really popular thing to talk about. How much carbon dioxide is being produced. Right now people are driving less, so less carbon dioxide is being produced, but you can calculate this, okay? And it starts with a balanced chemical equation, so you see the coefficients here, and then we recall that these numbers represent moles, okay? So that's really important because we're going to be dealing with lots of different things, grams, moles, maybe particles. We'll get to volume, so lots of things we'll be talking about, but if we're talking about the chemical equation, those are moles, okay? So let's double check here. So quick mole-mole conversions. If you have 6.5 moles of octane, and you have excess O2, so this is not a limiting reactant problem, so it's basically going moles of octane, how much water, okay? So we want to think about what we have and where we're going. How many moles of octane are consumed when 17.1 moles of CO2 are produced? So now this is going from CO2 to octane. So you can go reactant, product, product, reactant, reactant to reactant, product to product. This right here is stating there's excess, so this is not a limiting reactant problem. You only have to worry about one substance converting to something else. So go ahead and pause the video and do the calculations. What I'm emphasizing on these first questions are mole-to-mole conversions. Okay, so if you have moles of one thing, you need to go to moles of something else. You get that from the mole ratio from the balanced chemical equation. If you don't have a balanced chemical equation, you got to balance it because you need this mole ratio. So here you can see we're going to water, so 18 moles of water is on top, and we're coming from octane, so that's 2 moles of octane on bottom. And of course, sig figs, 2 sig figs, 2 sig figs. But the real key is pulling out the mole ratio. That's right here. The next one, same kind of question. If you're in moles and you're going to moles, it's all about the balanced chemical equation. We can just look at that and find the mole ratio. 2 to 16 in this case, 3 sig figs, 3 sig figs. Got another one for you. Moles of water are made in the combustion of 0.10 moles of glucose. So C6H12O6 is glucose. So again, mole ratio, that's what we're emphasizing here. 6/1 because we're going to water. If we're going to carbon dioxide, it would be the same, 6/1. If we're going to oxygen, it'd be the same, 6/1. But recall, this is stoichiometry. That's 1 mole here, 6 moles, 6 moles, and 6 moles. All right, so take a look at another one. Now we're in grams, okay? So if we think about our concept map, or where we're going here, now we got to get to moles converted to moles. So that takes us back to our grams, moles, and particles. So we have to feel comfortable finding molar mass, going here. If we were going in particles, we need that. In this case, we're just going to grams of something else. So that's grams, moles, moles, grams. That's your mole ratio. That's another molar mass. Okay, so this is what we need here in this equation, in this problem, and you got our balanced chemical equation. So the key is, don't get tricked here. If this is in grams of glucose, don't look at and just do a ratio. Okay, remember, you have to go to moles. And then if you're going back to grams, you have to follow that path to go from grams, then moles to moles, and then over to grams. So that's our roadmap. And so you can see here, we can see that mass, moles, moles, mass. That's what we're looking for in this roadmap. So go ahead and pause, calculate, see what you get for grams of CO2. And if you set this up, glucose, grams to moles, and then mole-mole conversion carbon dioxide, and then grams carbon dioxide, you should get 26.4 grams carbon dioxide. So this is the introduction of Chapter 7, what's a chemical equation, differences between chemical properties, physical properties. That leads us to our chemical equations, balancing chemical equations, and now just starting stoichiometry. So really encourage you to come to office hour if you want to work over this, because next video is going to be even more calculations for Chapter 7.